Our first panel is going to be on direct air capture and coupling it with sustainable building materials. My name is Simon Pang. I'm one of the authors for Roads to Removal. I led the direct air capture chapter along with several others in the audience who would be happy to speak to you more about some of our findings. I'll provide a very brief overview and then get into the panel and we'll have an interactive discussion with them. As JP mentioned during her talk, direct air capture is using chemical processes, using new materials to pull carbon dioxide out of the atmosphere, applying energy to those materials to release carbon dioxide in a concentrated form, and then storing carbon dioxide in some fashion, whether it be in geologic formations or using things like minerals to create solids. In Roads to Removal for direct air capture, really what we focused on were really large-scale opportunities for doing big direct air capture. And so, question is, well, what do we need to be able to do gigaton scale direct air capture? And a couple of things that I mentioned in the description. So we need the materials that go into the processes. We need a lot of energy. Dr. Sokolow mentioned we need a lot of potentially low carbon energy so that the X term in the 1 over 1 minus X isn't too large. And we need somewhere to put that CO2. And long-term, safe geologic storage is a demonstrated and scalable solution to be able to do this. And there's a lot of momentum in this area right now, thanks to efforts by the EPA and Department of Energy to get things like Class 6 wells permitted. Of course, we know these kinds of wells don't get drilled overnight. To be able to guarantee that these are going to be safe, that the carbon is going to be stored for long term, we want to make sure we get it right. And so this takes effort. While these kinds of things are being grown and being explored through things like the Carbon Safe program, which is designed to be a very rigorous program to look at different types of aspects of creating geologic wells, we need other things to do with that carbon dioxide. And so, JP mentioned that there's just on the Ohio side of the border, a Carbon Safe project going in. Simultaneously, while we are scaling up our ability to do geologic storage, we are scaling up our ability to do direct air capture. Again, the Department of Energy has funded 2 massive projects, the direct air capture regional hubs. These are down in Louisiana and South Texas. And so we are seeing a lot of development in these areas, both in the side of what do we do with the CO2 and the side of how do we get it out of the air. Of course, there are many companies beyond those involved in the direct air capture hubs and beyond those involved in doing geologic storage projects that are looking at deploying technologies primarily at smaller scale. It's a known technology or known class of technologies, direct air capture, but there's a lot of development that can happen, a lot of growth that can happen in trying to make these technologies cheaper, better, more energy efficient. And so, we need things to do with the CO2 that these smaller projects are creating. We need to be able to generate data from these projects and store that CO2. So in the near term, while direct air is trying to scale up, we're really asking what are the small scale opportunities that pair with the small scale direct air capture. And that's where things like mineralization of CO2 using building materials, using concrete can come in. And there are multiple companies involved in this kind of solution as well. So this morning we're going to hear from several of our distinguished panel members on aspects of the intersections of direct air capture and storing CO2 in building materials. First up, we've got Dr. Noah McQueen, who is a co-founder and the head of strategy at Heirloom.
Can you hear? Can't tell from this angle. Thanks for having me on this panel. As Simon mentioned, I'm one of the co-founders and the head of strategy at Heirloom. Heirloom uses a direct air capture process where that material we use to absorb CO2 is limestone. Limestone is about 4 to 10% of the Earth's crust and a relatively inexpensive material. So in terms of things that cost under $100 per ton, limestone is one of them. We use the limestone in a cyclic process where we put calcium carbonate, which is that limestone, into an electric reactor where we pull off its CO2 and produce calcium oxide. that calcium oxide's hydrated into calcium hydroxide, which becomes our sponge to suck up CO2 from the atmosphere. So one of the core innovations in Heirloom's process is we lay that calcium hydroxide out on trays, thin layers, expose that to the atmosphere. We've accelerated that reaction to happen in a couple of days, where in nature it happens over weeks to months. After it is reformed calcium carbonate, we can collect it again and continue that process in a cyclic manner. Very excitingly, late last year, we launched a facility in Tracy, California that captures up to 1,000 tons of CO2 from the atmosphere every year. And to Simon's point, we partnered with CarbonCure, which is a company that takes the CO2 from our process and injects that into concrete that lives now in sidewalks in San Jose, California. So it's been a really exciting partnership. What you'll notice is when you look at the map of available Class 6 storage or even demonstration projects, there are none located next to our Tracy, California plant. So in order to scale up this technology, while coupling ourselves to permanent carbon sequestration, we needed to work with folks who are involved in the built environment. So I'm super excited to talk to you today about Heirloom's technology and the intersection between built environment and direct air capture.
Great, thanks, Noah. Next up, we've got Dr. Marina Sophos, who is a program manager at Duke's Fossil Energy and Carbon Management Division within the Division of Carbon Removal.
Yeah, thanks for having me as well. This is a topic that's near and dear to my heart. I'm with FECM looking at our enhanced mineralization work. And before that was with ARPA-E, where I stood up a program on this topic of expanding the pathways from CO2 to building products and optimizing around the building product. And before that was with the Building Technologies Office. So, certainly in the department, we're looking at this space in terms of new opportunities where it can complement geologic storage, as was mentioned, as well as that dual use, angle where we have to make more building products. We continue to expand our built environment. We can't get away from, carbon-based products. And so let's take advantage of that. Let's see it as an opportunity, really, to be able to utilize the CO2 and try to hit both of our goals at the same time. The one thing I did want to kind of highlight just in the start here about how we think about this is from the embodied carbon angle of the built environment. And so this was mentioned earlier, right? We have to produce a lot of products, and in the built environment, historically, those emissions have been overlooked because they, frankly, the emissions associated with operating a building just, dwarf the emissions associated with constructing the building. But timing really matters, and that was highlighted by the presentation just now. And so a net zero building today that's constructed, it's actually going to most likely take well beyond 2050 to pay back the upfront emissions associated with constructing that building. And so oftentimes we think, oh, we're doing something good for the planet, but operational emissions are really reducing the waste associated with operating the building, and that we really kind of benefits on an annual basis. And the more efficient that building is in its operations, actually the longer it can take to pay back the upfront spike to make the building. And that gets put more when the grid becomes greener. And so there's really good analysis from Carbon Leadership Forum and RMI and others on that topic. And it's just something to really hone in on as well. But to get this to the scales that we talk about for building materials as a pathway to carbon storage, getting from maybe tens of megatons to hundreds or even a gigaton scale, we have to go beyond niche applications and pathways. And that requires, it's just as challenging as geologic storage in terms of like getting through all the regulatory hurdles. Our building codes are kind of a balkanized system that's implemented at the local and state level. And so I just wanted to end these remarks with really thinking about what is the value add. We actually have to not just meet the performance of an existing building material, but exceed to get it into the market. And so, we have there's a project here at Penn that's looking at Dorit will talk about that, is getting into that space. And that really, I think, presents an opportunity where we can improve upon as well.
Excellent. That's a great segue to Professor Dorit Aviv, who is an assistant professor of architecture here at Penn in the Weitzman School of Design.
Okay, hear me now? Good. Thank you for having me. As Chris mentioned, I'm an assistant professor here at Weitzman, but also direct the Thermal Architecture Lab, where we look at energy efficient buildings and path to decarbonization of the built environment. And while a lot of my work has been actually on operational energy, and by the way, to the question before from the virtual audience about the carbon footprint of being online, I've done a lot of work on data center energy efficiency, and they do have an enormous operational energy carbon footprint, or operational carbon footprint. They're 1% of energy-related carbon emissions. So that's actually a sector that really needs work. But increasingly, just like Marina pointed out, we're looking at embodied carbon because as the grid is shifting and electrifying, embodied carbon is becoming, a larger percentage of the building sector's carbon footprint. And I think everybody here knows that the building sector is notorious to be the leader in global carbon emissions. It's more than transportation. It's more than industry. So thinking about that and the future of the building sector, it's really important to start both like doing research and educating students on what is embodied carbon and how we can design for that. So from the research perspective, I've worked for the past 5 years on several projects that employ different strategies for thinking about the buildings as carbon sinks, turning them from carbon emission sources into carbon sinks, starting from the project that Marina just mentioned. She was actually involved in the first stages from the Department of Energy side, but it's a DOE ARPA Hestia project that aims at carbon negative buildings. Actually, some of the PIs are here in the audience too, Masoud Akbarzadeh and Shu Yang. Here, this building aims to reduce or to make building components that are carbon negative, both through the reduction of the actual amount of material with efficient structural design, and also with introducing bio-based materials and mineralization into the making of concrete. Shu has been working on introducing diatomaceous earth into the concrete to increase its carbon absorption. I've also worked again with Shu, and actually Stephanie Carlisle is in the audience here too, on bio-based materials in lightweight, and Masoud as well, in lightweight floor systems through an NSF Future Manufacturing grant. And actually just yesterday, my PhD student presented in Germany on a conference on his work on integrating living materials into buildings. That's another carbon storage strategy where he actually created biobricks that have plants and fungi help each other. I mean, the fungi help the growth of the plants. And this is happening with bricks that are specifically designed to help the plant growth and have hydrogel in them for the water storage. So on the education side, I also am in charge of the environmental systems courses for all the architecture students here at the University of Pennsylvania. And in the recent years, because we've realized how important it is for architects to start considering embodied carbon in their design, that we can't really make this change without architects actually understanding the implications of the materials they're using. we've introduced required workflows on life cycle assessment into the environmental systems courses that all architects have to take to do their professional degree. And there are other like specialized courses also offered in the school for life cycle assessment. Thank you.
Great. All right. And then last, we've got Christopher Neidel.
Yeah, my current affiliations are Open Air, Natural Resources Defense Council, the Four Corners Carbon Coalition, and the DAC Coalition, of which I'm on the board, which are relevant today. Most of the work that I do across all of those in some shape or form is I work on policy, particularly subnational policy, to advance CDR on the state and municipal level, which are really relevant. It was already said, where a lot of the regulatory changes that have to happen have to be done really at a more local level. Throughout the last 5 years of doing that, the intersection of CDR and buildings in the built environment has been really sort of at the core of that. I worked on a number of pieces of legislation municipally at the state level related to CDR and concrete, building integrated CDR as well. And I think what makes it so enticing, some of them have already been raised, is that yes, it's a place where you can store carbon in the short term as we wait for wells, but it's much more interesting than that. You know, it's certainly the embodied carbon piece in materials, but also as a operational platform for other forms of carbon dioxide removal, whether it's building integrated DAC or you're taking the waste streams from the building and you're using it for CDR purposes. But there's also a third one I think that's really important too, which kind of strikes at the kind of a core problem we still face, is really engendering the whole basic premise of CDR and why we have to do it. You know, and the fact that yes, we have to take carbon out of the air. We can take carbon out of the air. We have to put it somewhere, and in the process of doing that, we might be able to generate additional value that is separate from the climate impact. And so the third thing I think with buildings is they're a sort of a social and cultural and lived object through which you can embed and make that case. And I think we often think that it's, here's the industrial facility we have to put somewhere and point at it and say that's CDR, and we do have to do that. But in these early days, in terms of engendering that idea, which everything else rests on, political support for it, everything, if you can have that come to life in a building that people walk by or work in, or more broadly, the built environment, I think that that's a really important way to do it. Now, for all how enticing the built environment is, there's a tension because it has all of those potential hooks. There's so many different ways that you can do CDR vis-a-vis the built environment, but it's also consists of materials that are dirt cheap commodities. They're somewhat allergic to fancy things that add costs, and for good reasons. And for good reason, it's a highly regulated domain that, you know, people often put it on the concrete makers that they're so conservative and they don't like new ideas. Well, it's like, try doing their job. Who's going to stamp this fancy concrete that has, you know, calcium carbonate in it? So while the opportunity is vast, the challenges are quite unique and I think have to be kind of taken and addressed on their own terms. So, and an honor to be here.
Great. So I've got a couple questions here that'll get us started. Those of you here live in the audience, start thinking of your questions. If you're online, feel free to start submitting your questions. And, you know, I'll direct questions at a panelist, but if others want to chime in, please feel free to do so. So, you know, it's a good segue. So what are, thinking about some of the broader R&D challenges, what are those challenges when thinking about starting with carbon dioxide and putting it or other materials created from it into the built environment? I guess, you know, Dorit, maybe you can get us started off.
Sure, I can speak maybe more broadly on challenges that we've faced in thinking about carbon storage in our research projects. So there's two different sides to it. When you work on buildings, one is related to the fact that you have multi-functionalities for the building components. You know, so we're here all thinking about how buildings can act as carbon sinks or for carbon storage, but the building components have to have many other functionalities for the building to work, right? So, so one thing that in the Hestia project, in the ARPA Hestia project, we've come across is that as you're increasing the carbon absorption properties of the concrete, you're increasing the porosity of it with like, the diatomaceous earth. And then you're compromising other properties that are also needed, like the mechanical strength, like the thermal capacity of it. So there's actually, she's done a lot of work to actually increase then the mechanical properties and actually have them comparable with the conventional concrete. And so, and then I'm working with her on thinking about how this, how we can actually bring back the fact that concrete also works to reduce operational energy because it can act as thermal mass. But for that, you need it to actually be conductive. And if it's porous, it cannot be very conductive. So this is just to show you some examples that there are always trade-offs and that you cannot, you cannot just, it's very easy like to think about like one thing, but when we talk about buildings, it's a very complex system of functionalities that we have to consider. The other side of it is that, when we're thinking about building components, we also have to think about their entire life cycle. And that's something that's very hard to control. And we make a lot of assumptions when we think about, oh, they're going to be great for long-term carbon storage. Even when we think about wood, a lot of the wood actually gets burned at the life of the building. And if the building is not long-lasting, that's a huge problem because then it's not, it's not really acting as long-term carbon storage. So we have to make all these assumptions. And when we're developing a material, there are even more uncertainties. Like, how is this going to be transported? What are going to be the sites? Can this be manufactured locally to avoid the transportation emissions, et cetera? So, we need to develop a product, and there's just so many uncertainties about the life cycle, like the cradle to grave aspects of it when you're in the development stage.
I just wanted to add on Dorit's last point, because I think the end of life is really important and often overlooked. In the United States, the cheapest path at end of life is to tear down a building oftentimes, and it's because of the way we construct our buildings. And there could also be a bit of a misnomer there that sometimes. So UC Davis is doing some really interesting LCA work through the Hestia program, along with the University of Washington, and seeing when you crush up and grind that used concrete at its end of life, is it really it can end up having a significant footprint as well. And so it's not just a matter of extending the quote unquote the lifetime of the building itself, but each of those components and elements. And that, I think, is a really exciting research challenge as well of how can you repurpose, how can you push out that next emission spike and ensure that we're not just pushing the problem further out because we think we're locking it in. And oftentimes, to Dorit's point, these properties are orthogonal to each other. Maximizing carbon storage maybe is oftentimes sacrificing some of these other really important parameters.
Just one thing to add on to that too, which I think is kind of related in terms of a challenge. It's also buildings in the building sector have their own universe and set of standards around what constitutes being climate effective. Whether it's environmental product declarations or LEED. And we need a Rosetta Stone, I think, that's able to sort of bring carbon removal into the picture, because it's not yet really translating. So I do see that as a barrier. And there's certain things that, as we know, as we map out CDR opportunities across the life cycle of buildings, there's also certain things that won't be accounted for if there's a heavy emphasis on EPDs, which are the embodied carbon. Well, what about the cool stuff you can do with the waste concrete to extract the alkalinity for enhanced rock weathering or for, putting it back in other materials? So I think a big challenge we have, and there's some very smart people working on that. I don't know if Anu Khan is in the room, but I think a really urgent need is we need to accept that there's certain standards that are not going anywhere, that the architecture and the building community uses to quantify climate value. We need to figure out a way that we can hook ourselves onto that so that the impacts that we bring fully translate and are accounted for. So.
Great. And I want to pivot from R&D to a little bit of policy. So kind of building on that and thinking about strength of materials. So what's the role that building codes can play in getting low carbon materials or potentially even carbon negative materials into things like the market?
I know it's your headache that you guys have to deal with all the time, but from a policy perspective, I do something to add, but please, I'll let you first if you have something to say. Yeah, I mean, I think building codes are extremely exciting because you're starting to see municipalities, sometimes it's determined at the state level, sometimes it's more home rule, but where there are some leaders in this space, and I think New York City, largest city in the country, is on the cusp of this, of making the leap to creating global warming potential maximums for common building materials in the building code, not just for public procurement. So that's a massive platform that if we're able to solve the problem that I just described before, that creates an amazing opportunity for CDR, particularly when it's combined with, here's the line, the buy clean line that we have that says you cannot go above this global warming potential level. You can create levels of policy that say, well, what if you broke through and you go a 60% GWP reduction, which kind of implies in a lot of building materials that some form of carbon removal and utilization would be necessary, and create an incentive for that. So I think as we start to see building codes, Marin County, I think was the kind of the first one, Boulder County, there's a number of them, that is gonna be a hook that we're gonna wanna really look on. And they're everywhere. Every built environment has a building code, so there's a lot of targets to potentially hit to insert CDR.
Yeah, I think certainly the embodied carbon side of codes can play a significant role. And then there's the other side of it, which is the improvements that are constantly being made every 3 years to building codes from the operational emissions side. And it kind of goes back to that earlier point of if you can produce a product that actually exceeds, really thinking about what's going to be up in the time horizon 3 years from now, 10 years from now, in terms of meeting those operational emission requirements as well. That's really critical, right? To kind of ensure that you're going to have the market entry. If you can show that you can exceed that or provide a value add, that becomes really exciting as well, because the policies are rare right now to pay for that premium unless it's in the form of a stick that you cannot exceed this. And if you can provide a little bit of that carrot in terms of the product you're providing, that's very significant as well.
All right, well, keeping an eye on the time, let's go to some of the questions. Maybe we'll start with one online. Emma, if you want to. Yeah, and then we'll take questions from the room as well. I'll ask folks in the room to introduce themselves as well before they ask their question. Thanks.
All right, great. Thanks, Simon. We've got an online question here. It seems that existing materials recycling isn't as well integrated into the building and products manufacturing process as it could be. Can the reuse of resources that require intensive environmental impact, like mining and oil drilling, be included in the capture byproducts?
That's a really interesting question, because one of the ways that we think about the intersection of building materials and direct air capture is the limestone. So limestone is one of the largest inputs, if not the largest input, into the cement and concrete making process. So you can think, after you cycle this through direct air capture, you could upcycle it into the cement making process. Maybe you can use byproducts, as Chris mentioned earlier, from the demolition of buildings, can grind that cement material, concrete material, and do enhanced rock weathering. So you can actually use these materials in a multi-purposed way that allows you to reduce the embodied emissions associated with the building materials in the first place.
Yeah, I think that's a good point. The LCA really matters, though. And these are really promising pathways when also considering how can I the efficiency of the processing itself and make sure I'm not just pushing the problem out or creating a problem. Because in some instances, the numbers look really good, and in others, they can actually look worse.
Yeah, I would also add to that too, that a lot of the biggest embodied carbon burden for any built environment are in materials that are inherently locally produced. And concrete, asphalt. And then within cities, the whole narrative and discourse around circular carbon and circular carbon economies is really kind of taking hold a lot. So I think you have like a receptive audience to the basic idea. Imagine if we could take what is the largest part of an urban waste stream, which is demolished concrete, and repurpose that into something that adds value, and it all happens within a local circle. We have the basic building blocks of doing that with those two materials. So it's not like a big jump, I think, at least in regard to those two, to propose a vision that includes incorporating carbon in those materials.
Julio Friedman, Carbon Direct. Lovely panel, thank you all. The flip side of building standards is procurement mandates. And this is another government policy. Governments build a lot of, structures using concrete, steel, using potentially materials. Is there a way, Chris, I know you're already on top of this, but is there a way not only to get more governments to buy more CO2 removal as part of their building strategy, but also to incorporate CO2 procurement purchases in their own practice?
The two people I want to name check. So the idea, the initial legislation that we worked on, which was a concrete procurement one, came from a conversation I had 5 years ago with Julio, where he recommended it. We've been buddies ever since. And I think what you said, your first comment today was really great, I think, about visualizing the sort of the future that we want, and how do we take the idea that carbon physically is a building block of doing that. I think that was a really great thing that you mentioned. Yeah, I think there's a lot of different ways. I mean, concrete in particular, it's upwards of 40% is purchased by the public sector. That's unique. A lot of times when procurement is leveraged, it's more for symbolic first actor. Let's put it on the town hall or solar panels, but it's not a meaningful impact that it actually really has on driving markets. That's not the case with things like asphalt, which are almost exclusively used paid for by governments, and concrete. So they have an ability, if they become an early adopter and an early actor, through their own procurement standards, that is a big piece of the market, and that can have a ripple effect more broadly, and then it can lead to other things, like if you've already done the brain damage around what constitutes low carbon concrete for your procurement, that can then inform what a building code type of standard would look like. So I think states and cities can do that. You have places, California, unfortunately, cement and concrete were excluded from its Buy Clean, but you have places like Portland, Oregon, which was one of the first to have a low carbon concrete standard around that. New York City as well. One idea I'm really excited about, and Julio, I'd love to get your thoughts on this at some point, is the idea where we don't want just to get the incremental, okay, you're going to use more slag or you're going to not specify as much cement. We want these breakthroughs that actually happen. So there's where an advanced market commitment, if you had a public sector where, let's just say the state of California or the state of Colorado said that we're going to give a extremely high advantage, as long as it fits within a certain cost parameters, to a concrete that comes in with a 60% reduction GWP. You could do that, and then when you have the interaction between local and state, which is really significant. Cities are usually just follow what the DOE comes up with standards and specifications, but you could really aggregate and have almost like a Groupon where the state does the more sophisticated program design around that, what the terms are, but they can say, we're going to get the 5 or 6 largest municipalities to also join suit and add their demand to it too as well. So for a material like concrete, that really adds up. That really becomes a market driver. Don't know if that answered your question, Julio, but that was what I thought of when you asked it.
I want to go one level a little bit deeper and go into the people that would participate in that Groupon. Dorit, I'm wondering if you have any thoughts on how to get architects and structural engineers to engage more with these kinds of materials as the folks that would be procuring them.
Sure. I mean, I think that a lot of it is just education and engaging people, because I think architects are actually excited to be able to make an impact, and they are just really not considering this at the scale that we need them to. And I think, the choice of materials, if it's, sure, you're working with clients, so there's always the question of cost. But if you get some of these products to be at a cost that's, and maybe there are incentives to do that, right? Like we're seeing with other type of like climate mitigation strategies where the government gives incentives. But if architects can actually specify materials, some of these things are not even visible. They don't even affect the design. Like insulation materials can make a huge impact, switching from ones that are very emission intensive to bio-based materials that already exist at scale. But we just need to make architects more aware of it. So I think, you know, just there are a lot of already courses given to architects by the Professional Association of Architects, AIA, about this topic. But really, I think starting with when they get their professional degree and it's just recent that we started implementing these LCA courses, but I think this generation is going to think about that when they specify building materials.
Yeah, I would add, as architects become more familiar with these types of materials, and we, you know, start to kind of better integrate material choice with design decisions, there's an opportunity to even go beyond that. And I'll you know, just mention again, give a shout out to Dorit and Masood and the team, because that's one example where they're designing this funicular structure. They're actually taking advantage of the carbon storage properties of the material and building that from the beginning into the design process. And so now you can imagine higher performing buildings. You can start to be more creative in the ways in which we leverage those properties. So it's you know, it goes beyond just storing the carbon of how can we maximize that carbon storage potential and take advantage of it.
If I could also just add, not to embarrass or make you blush, Dorit, but I think that the architecture field is so critically important and interesting as a sort of a deliverer and shaper and almost alchemist, I think, for carbon removal, but it's completely overlooked. You know, it's this unique field that has this blend of poetry, aesthetics, vision, narrative, but it can't fall down. It has to work. It has to be built on time. It has to be done according to schedule. And they interact with all stakeholders who have to make decisions from a procurement perspective, from a buyer. And we're seeing really interesting signs of that right now, not just in academia, but in practice. And so I think we really need to really work on not just thinking about how we embed CDR in things, but in the professions that make those things happen. I think architecture is one of those hotspots that we absolutely have to really, really focus on. So looking forward to talking to you over lunch.
Might add just one more thing, but it goes full circle because then you have to consider the materials of construction for the facilities that do carbon removal. So when you look at some of the biggest hotspots for embodied emissions in something like a direct air capture facility, you're looking at concrete, you're looking at steel, you're looking at plastics, all of which create these facilities that take CO2 out of the atmosphere. So like the architects that we work with think very holistically about that life cycle analysis to identify those hotspots, and we work with them to try to mitigate those emissions. So it's very critical in a lot of different ways.
Great. All right. I think we're going to take one more question from online.
All right, this is a quick question. If any of you guys know the answer of, or if it's been measured, the potential scale of CO2 removal that could happen by incorporating these things into building.
Yeah, so when we were developing the Hestia program, we did some back of the envelope calculations, very conservative. That was in the hundreds of megatons. I think there is a representative from RMI here. They're working on a report that is going much more in depth and looking at the potential in a wide range of scenarios. And I think kind of overall, if we're able to get all things right, we can, you know, hit that beyond hundreds of megatons to gigaton scale. Yeah, I'm looking forward to that report coming out.
Yeah, I think Sabine Fuss, who's a very notable IPCC scientist, in the spring published a paper with a bunch of other scholars trying to quantify what the potential for carbon removal is in the urban environment, not specifically on a building level. So if you Google that, that's a pretty interesting read.